Hi, chemists. We talked last time about calculating the pH of acids. We know that you can get the pH by taking the negative logarithm of the concentration of H+. We also know that bases have a pH that's higher than 7, but it's not obvious why that is, right? Why would a base that gives off OH minus affect H plus at all, and why would that then change the pH? So we're going to talk today about how to calculate the pH of bases. But first, we need to really understand what an acid and a base actually are.
Okay, so an acid is something that gives off H plus. For example, right, H2SO4, sulfuric acid, can lose two H pluses. And then you have SO4 2 minus left over, right? And remember, if this is happening in water, these two H pluses are immediately going to bond to water molecules to form H3O plus, right? You never actually have H plus alone by itself. We also know that a base gives off OH minus. So for example, KOH, potassium hydroxide, is an example of a base. When you dissolve it in water, it splits, it dissociates into K plus and OH minus. If you want to know if something's an acid or a base and you're not sure, one thing that you can do is you can check your reference table. So table K lists a lot of the most common acids, and table L lists a lot of the most common bases. And some of you actually already noticed something a little bit odd about our list of common bases, right? There's one of these common bases that's not like the others, right? And that's NH3. It's a little bit confusing why NH3 is listed as a base because it has hydrogen in it and it doesn't have OH minus in the chemical formula, right? So NH3 isn't actually a base according to this definition. But it is considered a base because when you dissolve it into water, it reacts with the water. And when NH3 reacts with the water, it actually grabs a hydrogen and forms the ammonium polyatomic ion, which you might remember from when we talked about polyatomic ions, right? So NH3 grabs a hydrogen off of water. That means what's left over? Well, OH minus, right? Water that's lost a hydrogen. And so even though NH3 doesn't have OH minus in its chemical formula, when you dissolve it into water, you end up with OH minus because NH3 steals one of the hydrogens from the water molecule. NH3 doesn't quite match our definition of bases. So we actually need a better new definition of bases. This definition of acids and bases was developed by a chemist called Arrhenius. And it turns out that Arrhenius was actually erroneous, right? This definition of acids and bases is a little bit too narrow. So a pair of chemists called Bronsted and Lowry developed a more general definition for bases. They said, okay, well, a base could be anything like NH3, right? NH3 doesn't have OH minus in its formula, but it's a base because it grabs hydrogen off of water, leaving behind OH minus. So a base is anything that accepts H plus. Or another way to say that is since H plus is really just a proton, they often will refer to bases as proton acceptors. And so a base is anything that accepts a proton, right? That means NH3, that means pretty much all of the amines from organic chemistry, so molecules like CH3 and H2, right? And pretty much any other amine will react in exactly the same way. It'll react with water to grab H plus. So this would form CH3 and H3 plus, right? It would be positive, and then with a leftover OH minus, right? So any amine, and then any Arrhenius base is also a Bronsted-Lowry base, right? So for example, like when we think about KOH, we can think about KOH just losing OH minus, but we could also think about what happens if KOH comes into contact with H3O plus from an acid. If KOH comes into contact with H3O plus, it's going to steal a hydrogen off of this H3O plus. You're going to end up with K plus, the OH minus and the H plus will bond together, and then this H3O plus will become another just plain water molecule. So you're going to end up with K plus and then 2 water molecules, one made from OH minus and H plus, and then one made from the leftovers of this molecule. Right? So any Arrhenius base, right, any ionic compound that has OH minus in its chemical formula is also a Bronsted-Lowry base. Bronsted-Lowry's definition is a little bit more general than the Arrhenius definition. So every Arrhenius base is a Bronsted-Lowry base, but not every Bronsted-Lowry base is an Arrhenius base, right? NH3 is not an Arrhenius base. Cool. Bronsted and Lowry didn't really change their definition of acids. They would usually phrase acids, instead of saying gives off H+, they would usually say it's a proton donor, but of course that's basically the same thing, right? Giving off H+ and donating a proton is basically the same thing. So really Bronsted and Lowry developed our definition of bases rather than really having much change with our definition of acids. It turns out that some substances are what's called amphoteric, which means they can act as an acid or a base, right? Water is one of those. So water can react with itself, and I'm going to use 2 different colors to kind of show what's going on. Water can react with itself, right? When water reacts with itself, one of these water molecules can grab a hydrogen off of the other water molecule. So this H2O could grab a hydrogen from this molecule, right? This molecule would lose a hydrogen, and so it would end up as OH minus because it just lost its hydrogen, right? This is an example of a reaction in which water is acting like both an acid and a base, right? Let's think about which of these waters is acting like the acid and which one's acting like the base. So remember, acids lose H+. So which of these molecules lost H+? Well, we can see in the products, the blue one is the one that lost the H+. So this water is the one that's acting like an acid and losing H+. The other water is gaining H+. So this water is really acting like a base. And I've written this chemical formula weirdly because I wanted to show the water bonded to the hydrogen, but really water bonded to an extra hydrogen is just hydronium, H3O+. This equation is called the autoionization of water, and it's a super important equation. So let's go ahead and rewrite this a little more neatly. All right, so here's my equation for the autoionization of water. If we think about this word autoionization, this prefix auto means self. You might be familiar with like an automobile, right? An automobile is basically a self-moving cart, right? So instead of having a cart that had to be pulled by a horse, it's a cart that pulls itself and moves itself. We know that an ion is a charged particle, right? A charged molecule or a charged atom. So when we're talking about autoionization of water, that means that water is turning itself into a charged particle. So the water is reacting with itself to form H3O+ and OH-. This reaction is in equilibrium in every sample of water that you'll ever encounter. And so it turns out that it's actually literally impossible to ever have a sample of pure H2O, because even if you have nothing dissolved in it, even if you remove every single other ion, water will react with itself to make H3O+ and OH-. Now, at equilibrium, if you have a neutral solution, right, the concentration of H3O+ is pretty small. We can actually calculate exactly what it is, right? If we have neutral water, we know that the pH is 7. So let's figure out what the concentration of H3O+ would be based on that pH. using the pH, we know that the pH, that's 7, would equal the negative log of the concentration of H3O+. So we can multiply both sides by -1. -7 equals log of H3O+, or you could write in log of X if you prefer. To reverse the log, we would take 10 to the power of both sides, right? This log is saying 10 to this power equals this variable. So 10 to the -7 power equals the concentration of H3O+. So in a neutral solution, this equilibrium is happening, but it's happening very, very smallly. It's happening not very much, right? You're gonna have a lot of water and only 10 to the -7 molar concentration of H3O+. Let's think about what the concentration of OH- would be in a neutral solution. Well, based on this chemical equation, for every 2 waters that react, one of them is going to gain a hydrogen and form H3O+, and the other one's going to lose a hydrogen and form OH-. So however many H3O+s you have, you're going to have the same number of OH-. So the concentration of OH- is going to be exactly equal to the concentration of H3O+. In a neutral solution, the acid and the base are both going to have a concentration of 10 to the -7. That's not true if we add an acid or a base to our solution. So let's think about what happens if you add base to your solution. If you add a base to your solution, this equilibrium is going to shift. We've talked about that using Le Chatelier's principle. So take a minute to think about which direction the equilibrium will shift and what's going to happen to the concentration of H3O+ if we add OH-. So based on Le Chatelier's principle, if we add OH-, the equilibrium is going to shift to the opposite side, right? The reaction is going to try to counter the change by using up this OH-. So if we add a base, and meaning we're adding OH-, that OH- is going to get used up and make more H2O. So the equilibrium is going to shift towards the reactants, and that means as this OH- is getting reacted, it's reacting with H3O+, and so the H3O+ is getting used up. So the concentration of H3O+ will go down. So anytime you have a basic solution where you add a base, that's going to decrease the amount of H3O+. That's going to also change the pH, right? If this is now lower, the log of this would be lower. The negative log of that, if log goes down, the negative log would actually go up. So when this concentration goes down, the pH will go up. In other words, when we add a base, we're increasing our pH. So that means as the concentration of OH- increases, the concentration of H3O+ will decrease, and vice versa. As the concentration of H3O+ increases, the concentration of OH- would decrease. So if we had an acidic solution where we added a bunch of H+ that turns into H3O+, that would decrease the concentration of OH-. So acids and bases are essentially opposites because they have this inverse relationship. The more H+ you add, the less OH- you're going to end up with. The more H- you add, the less H+ you're going to end up with. One useful measurement when we're dealing with bases is to think about, instead of pH, pOH. pH is the negative log of H+. So in a similar vein, pOH is really the negative log of the concentration of OH-. Let's think about what happens if pOH goes up. If pOH increases, that means that this whole side of the equation is increasing. That means if we deal with our negative side, if we consider our negative sign, that means the log of OH- would have to decrease. In order for the negative log to increase, the log would have to decrease, which means OH- would also have to decrease. So if pOH goes up, that means the concentration of OH- is going down, which means our solution is becoming more acidic, right? We're having less base and it's more acidic. And so if it's more acidic, the pH would also decrease. So pOH and pH have an inverse relationship. We can actually relate them exactly using this equation. pH plus pOH is always equal to 14. We can check for a neutral solution. For a neutral solution, the pH would be 7 and the pOH would be 7, and so they'll add up to 14. If we have a basic solution, the pH will get higher and the pOH will get lower. Let's look at some examples because this is mostly useful when we're actually trying to solve problems. So let's look at this first example. I want to calculate the pH of a 0.1 molar sodium hydroxide solution. So in order to calculate the pH, the easiest way to do this is actually to start by calculating the pOH, right? Because I don't directly know the concentration of H+, but I do know how much OH- I have. But a 0.1 molar sodium hydroxide solution would dissolve and form a 0.1 molar OH- solution, right? So I can calculate the pOH by doing negative log of the concentration of OH-, which in this problem is negative log 0.1. Okay, the log of 0.1 is saying 10 to what power gives me 0.1, right? 0.1 is 1/10, so 10 to the negative 1 gives me 0.1. So this is going to be equal to negative 1, aka 1. So I have a solution that has a pOH of 1. If I want to know the pH, that's what the problem's actually asking me for. I know that pH plus pOH equals 14. So my pH is going to be 14 minus 1, aka 13. And it's always worth checking, does that answer make sense? I have a basic solution, so I'm expecting to have a pH above 7. So this answer makes sense as an answer to this problem. Let's look at another problem. So I want to know the pH of a 0.001 molar KOH solution. See if you can figure this one out on your own. All right, so this solution is going to be 0.001 molar OH- as well. I can similarly calculate the pOH by doing the negative log of that concentration of OH-. So I'm going to be doing negative log of 0.001, right? Now, okay, 0.001, that's really 10 to the negative 3. So so when I take the log of that, it's like 10 to what power is 10 to the negative 3? Negative 3. 10 to the negative 3 is 10 to the negative 3. Okay, so the negative log of this is negative 3. So I've got negative 3, aka 3. That's my pOH. My pH plus my pOH have to equal 14. So my pH is going to be 14 minus my pOH, 3. So my pH in this problem is going to be 11. And again, this is a basic solution, so it makes sense that my answer should definitely be above 7. Let's look at one more example problem. This one's a little bit tricky. Okay, so I want to know the pH of this 0.02 molar solution of calcium hydroxide. First of all, it's worth realizing when calcium hydroxide dissolves, it's going to form Ca2 plus 2 OH-, right? For every mole of this that dissolves, you get 2 moles of OH-. So if I have a 0.02 concentration of this formula, that's really 0.02 times 2, right? That's really a 0.04 molar concentration of OH-, right? Since the molarity of the OH- is double whatever the original molarity of the calcium hydroxide was. Cool. I can figure out the pOH by doing the negative log of that concentration. So the negative log of 0.04. Now this is something I would need a calculator for, right? I can't do this in my head. So I'm going to go ahead and plug this into a calculator. And I get, for log of 0.04, I get negative 1.4. So overall, this is going to be negative 1.4, aka it's going to be 1.4. The pH is now going to be 14 minus that pOH. And so I'm going to end up with a pH of 12.6. if we know the concentration of any base, we can figure out the pOH, and from that we can figure out the pH. And if we wanted to, we could even figure out the concentration of H plus by reversing our log, right? Multiplying this by -1 and then taking 10 to that power. So if we know any of those values, concentration of H plus, pH, pOH, or concentration of OH minus, we can find any of the other three values. So that's what you'll be doing for homework for tonight.
All right, so that's how you calculate the pH of a basic solution. On Monday, we're going to be doing a lab experiment using our purple cabbages. I'll go ahead and post a video that Mrs. Whedon made so that if you want to, you can get started over the weekend, but it's not due until Tuesday. There's normal homework and normal worksheet due on Monday, Sunday night. If you're not able to do the experiment on your own, or you don't want to like stink up your apartment by cooking some cabbage and get all your family members mad at you, you can also come to office hours on Monday or Tuesday, and I'll do the lab live, and you can, heckle me while I'm doing it. All right, so I will see you next week. Looking forward to actually getting to test out some acids and bases with you.